Hello, students. Last homework set, 7.5. So a couple of these start off with arranging numbers, kind of put things in order. So don't forget, you can always write out numbers, especially if you have a repetend. But if you get to some type of funky square root, just grab your calculator or your cell phone's calculator is fine. All right. So we start off with writing an irrational number whose digits are fours and fives. We did one in the video of ones and twos. So again, you could 1 2 1 1 2 1 1 1 2, and it continues like that. That's an irrational number whose digits are ones and twos. Could be 2 1 2 2 1 2 2 2 1. Could be 1 2 1 1 2 2 1 1 1 2 2 2 dot dot dot, right? So you have all those options. Um, yeah, I mean you can mix it up. You can say 1 2 2 1 2 2 2 1 2 2 2 2. I mean, again, you can use your imagination, but it just cannot be in a way that repeats digits. It can have a pattern, but it cannot repeat digits in a way that you could put a bar over the top. Pythagorean theorem. So remember Pythagorean theorem. This is from prior coursework, possibly, or we've also used it a little bit in this class. But a squared plus b squared equals c squared. We're going to do more with this and even show you why this is true, where it comes from when we get into Math 106. So anyway, small side, small, and big is kind of how you think about it. The big side is often referred to as the hypotenuse. But as you're finding missing pieces, so for example, in part B, you could say I have 3 squared plus 3 squared because those are the small sides, and the long side would be on one side by itself. Solve that one, and then remember when you do take the square root, it'd be the absolute value, so you'd get a plus or a minus. But in this case, because we're dealing with length, the negative answer can kind of be ignored. So keep that in mind. All right, so arrange in order. So again, take your calculator, find a decimal approximation for this number, and then off you go. And what's interesting, of course, is that when you take the square root of a number, like the square root of 1/4, it's really the same because of the way the roots work as the square root of 1 over the square root of 4, which becomes 1 over 2. So this is a strange situation. The square root of a number gets bigger, right? It actually got larger than what I started with. Now, normally we're used to numbers like the square root of 25 is going to be 5, which is much smaller. But think about that. The check for this would be 5 times 5. And if you multiply two numbers that are bigger than 1, it's going to get larger. If you multiply a number like 1/2 with it is less than 1, it's going to get, not surprisingly, smaller. That power of 1 is just amazing for this class. Let's see here, number 4, determine which of the following represent irrational numbers. So again, if you can get, like I just showed you, square root of 25, if they said square root of 25, you can write that as 5. 5 is a natural number, a whole number, an integer, and a rational number. So since it meets all of those, it is not irrational. Let's see here, find if possible the following principal square root. So again, principal square root is the positive or non-negative root. So it's actually the same as the one below it. It's the same symbol. Let's see here. Find the approximate principal square root using squeezing method. Again, if you're looking at this number, then 1.64, it says rounded to the hundredth. So 1.64 has got to be between 1 and square root of 1 and the square root of 4. So we're finding the square root of this, which means square root of 1 is 1, square root of 4 is 2. So we know the answer has to be between 1 and 2. And then you can use the squeezing method to kind of approximate. Go 1.4, is that too big? Go 1.3, is that too big? And you'll see pretty quickly you'll get to like 1.2 is less than the square root of 1.64 is less than 1.3. So I'll get you to that stage. Your goal is to get down to hundredths. I've got you down to tenths. Okay. Let's see here. Classify as true or false. Wow, always, sometimes, never. This is, you can see it coming, right? If false, give a counter example. So, go ahead and treat these like always, sometimes, never is good practice. The sum of two rational numbers is a rational number. So a over b plus c over d, is that a rational number? Question mark. The sum of any two irrational numbers is an irrational number. Okay, interesting. Wonder, wonder, wonder. But if you remember how we wrote our ones and twos, if you did the same with kind of alternating those, then maybe you'd end up with something when you add them together that's like 0.33333333 forever. Maybe there's a push in the direction for that one. All right, let's jump forward. And let's see what comes up next. What questions did I have to do on this? 1 through 8, 10 through 14, 16, 18, 20. Okay, 1 through 8. So find 3 pairs of irrational numbers between. There's infinitely many pairs. All right, even between these that look like they're so close together. Just remember 0.55 repeating, 0.56 repeating. This one could have even been shortened to 0.5 repeating, but you just need something that's between them. So start writing a number that has to be between them. So this is 5s forever. That's a 5, 6. So make sure it's less than 5, 6, 5. So you could say 5, 6, 1, and then you could continue with what we did before. And this would be an irrational number that's definitely between them. But it didn't have to be 5, 6. It could have been 5, 5, as long as it's bigger than 5, 5, 5. It has to be between them. So just make sure your numbers are between them. Let's see here. That was 8. Right. Let's see here. I've already forgotten 10 through 14, 16, 18. Okay, so 10 through 14. So now you get to use your set notation. So let's go back to chapter 2. When you intersect two sets, try to use the symbols that we have. R for reals, Q for rationals, I for integers, W for whole, N for natural, and S for irrational. If you take the rational numbers and you intersect them with the integers, where do those overlap? What types of numbers would you see that are contained in both of those? Okay, and so put an equal sign and put a symbol up here that represents what your value is. Let's see here, 11. Oh, got it. So 11 and 12 are very similar. You are tasked with finding which set a number is in, and then which set the solution is in. Like down here, there'd be a solution to these. So let's start with a different one. So let's start with like the number 5. If I start with the number 5, 5 is a natural number. It's an integer. It can be written as 5 over 1, so it makes it rational. And because it's rational, that makes it real. Because it's rational, it cannot be irrational. So that would be the markings that I would put down for the number 5. If I had the number -7, -7 is an integer. -7 over 1 is a rational number, which makes it real. Because it's rational, it cannot be irrational. And because it's a negative number, it cannot be a natural number. So you're just putting check marks as you go through. Okay. So again, if you had a number like 4.75, not one of the ones listed here, but 4.75, you'd have to say, I'm sorry, 4.75 is not natural and it's not an integer. It is rational though, and that makes it real, which also means it is not irrational. Okay. All right. Let's see here. Moving on down. I said 13 and 14 as well. So 13 is determine which real values the statement is true. So yeah, this is your chance to kind of explore. This links back to chapter 5. You'll notice here we have a square root of what some people would say is negative x. But when we don't know what x is, we don't say negative. We would say the opposite. And if you say and you think about that as the opposite, then it doesn't seem like it has to be a negative number. What goes under the square root in order to maintain a value, this thing, this cloud, must be non-negative. So that's true. So it could be 0, it could be positive, it just can't be negative. So when I take this and chuck it underneath here, so that I have this, what looks like negative x, if I say negative x, my mind thinks it must be a negative number. But x is an integer, so x could be, and actually I said for what real values, so x could be even an irrational number if we needed it to be. But again, it goes in there. It could be positive, could be negative. Okay, just remember that. Down here, 14 square roots form these. Oh, yeah. Okay, so now you get a chance to simplify square roots, which seems like a concept from higher level algebra. What I'd like to do is show you that this is basically just division. So if you've struggled with this in the past, just understand I'm about to show you a cool way to integrate division into something that seems super challenging. And you also get a chance to see why it's so important. The fundamentals that you're teaching, if you are teaching a younger grade, the fundamentals are so critical. We use them in a lot of additional classes, algebra classes, advanced algebra classes, pre-calculus, and so forth. Those fundamentals will carry a student through. So let's take a look and let's do a square root of, uh, I have no idea. What should we do? What do you feel like, self? Let's do 3,200. Okay, 3,200. So the key to this technique is realizing, first off, that when you have a root, there is an index here. And if there is no number written there, the index is 2. Okay, we're going to need that. Then you need to take your number and prime factor it. Okay, it's usually easiest to prime factor. Some teachers will say, find the square roots that are in there. Break it down into find perfect roots. I got to tell you, that's not easy to do, especially if you're factoring. So if you see this as a 2 in it, 2 is not a perfect square. Okay, it takes a while for you to see that there's actually a 64 in here, which is a perfect square, but I don't think it's quick. Like the division and the factoring would be very challenging. So instead, come over here and do something like 32 times 100 and just prime factor this. This is like 8 times 4. This is 10 times 10. 8 times 4 is 2 times 2 times 2. 4 is 2 times 2, and over here I have 2 times 5, and over here I have 2 times 5. So at the end of the day, 3,200 is equal to the square root of 1, 2, 3, 4, 5, 6, 7, 2. So I'm going to have 2 to the 7th power, and then 5 and 5 becomes 5 squared. Now I'm going to show you kind of the what some of you might think of the long way, but it's going to show you all the steps that are really taken in this process. And then I'll show you kind of a shorter way that I think will help you as you go through other problems. So once it's prime factored, I can think of this as 2 to the 7th times 5 squared, all of it raised to the 1/2 power. That's where that index comes in. Okay, so if this was a cube root, my index would be 3. This would be to the 1/3 power. Okay, now use your property of exponents to distribute. So you have 2 to the 7 halves times 5 to the 2 halves power. And then we'll simplify a little bit, but this is where division, I said it was division. This is where division comes in. This exponent, you can think of it as 7 halves. You could think of it as 7 divided by 2. See, 7 divided by 2 is going to give you 3 whole times in there, right? 3 times 2 is 6. And it leaves you with a 1/2 power. So if you combine these again, you multiply the same base, you're going to add, you get 3.5. So that 3.5 is split up right here. The next one, 5 to the 2 over 2, is just 5 to the 1st power. So now I'm going to put all of my whole number exponents together. This is 2 cubed times 5 to the 1st. And what is left behind is a 2 to the 1/2. And my final result would be 2 cubed, which is 8. 8 times 5 is 40. And 2 to the 1/2 becomes the square root of 2. Most of the time we write it without the multiplication symbol, and this would be known as simplified radical form. Right? Simplified radical form. Very cool. But how can we get there quickly? So what I want you to do is come back up here, and we're just going to do the division. So watch this. If I bring this over and I say, okay, I've got the prime factorization times 5 squared. My end result will be, because this is a 2, 2 goes into 7 3 times, and it leaves me a remainder of 1. So leave the remainder of 1 piece under the radical. You're going to get back to it anyway, just leave it under there. Then 2 goes into the exponent of 2 here 1 whole time, and there it is. There's your final answer. It's 8 times 5 times the square root of 2. So you can get there very quickly by thinking of this as division, which, as I just showed, it is. And so that's a really powerful tool. In my mind, I think that's one of the biggest tools you can have is how do I link what I've already know into something new? But it allows you to do things that probably would have seemed nearly impossible before. So let's do this with a cube root of 2 to the 7th, 3 to the ninth, 5 to the 14th, right? I mean, we're just gonna go crazy here. 7 to the um 40th. Why not? Okay, so all right, so if I was simplifying this, this looks amazingly challenging. And again, if you were using a different teacher, they might say, well, try to find all your perfect third roots. Um, no, I will not do that. I will spend something that does not take that much of my time. Three, think about it. Three as your index is going to be the power of 1/3, and then each of these is going to be thirds as exponents. So you're really just dividing 3 into that 7. So how many times does 7 get split up into 3 groups? And you'd say, okay, well, wait a minute here. 3 goes into 7 2 whole times. So you use a 2 exponent out here for 2 whole times. There's 1 left over, so leave the 1 left over under the radical. When I taught this in an algebra class, I called this dumpster diving. And so underneath here, you can think of it like this is a dumpster. It's got a whole bunch of pieces. And what you can do is if you're dumpster diving, you can find pieces when they all fit together. It makes the item. You can go sell that on eBay or something. So here I had 7 pieces that kind of make up twos, but the 3 says I have to make groups of 3 out of them. And so I make the group of 3. I can make 2 whole objects, and I leave 1 piece behind in the dumpster because I couldn't use it. Next up, use the 3, and 3 goes into 9. It goes in 3 whole times. So I would have 3 cubed. Next up, 3 goes into 14. Okay, I got to think about this. 3 goes into 15 5 times. So 14 must be 4 times. So 3 would be 5 to the 4. Then let's check that. 4 times 3 is 12. Oh, that leaves 2 pieces behind. Okay, so I have 2 pieces left in the dumpster. And the one for 3, it had 9. 9 went into 9 and 3 worked perfectly, so there was nothing left for the dumpster. And lastly, I have 7. So how many whole groups can I make? Well, 3. Now 3 is going in kind of cutting up 40. And so if you go back to what we did earlier, you can think of 40 as 30 plus 10, because you can then see obviously it goes in at least 10 times. And over here, you can see this as 9 plus 1, and it must go in 3 more times. So 10 times here, 3 times here, that's 13 is my exponent 13 times. 13 times 3 is 39, leaves me with 1 remaining. So I put that in the dumpster, and that is how you can simplify radicals very quickly. And I mean, look at that. That's very quickly. So again, when you do the division, the whole part comes out, the remainder stays underneath. So pretty cool technique. And I'll give you a couple here that you can try that on as you do it yourself. Okay. 12 through 14. Yeah, you could do it on the other one. You could do it down here, like on a 6th root of this or on a cube root of this. I mean, you absolutely could. I think it's kind of a cool technique. Let's jump up to the top because I think 16 is my next. A geometric sequence. All right, so how can you turn this into something from this section? Well, you started with 4 and you had 2 spaces in the middle, and then you have to end with 8, but I'm going to leave that as a second space. We know this is 8, but let's see what it looks like because a geometric sequence has a common ratio. So you'd multiply by the ratio to get 4r. Then you'd multiply by the ratio again to get 4 times r squared. And you'd multiply by the ratio again to get 4r cubed. And you know that that last term is 8, so you create an equation that says 4r cubed equals 8, and then you solve that equation. Okay, there you go. Same for part B. In part C, you could actually tell the ratio because you have 2 terms right next to each other. So you actually know it's 2, and I multiply by the ratio, and that gets me to the square root of 2. So if you're trying to figure out what r is, you can just divide. So don't make it harder than it needs to be. It turns out this is 2 over the square root of 2. That's the ratio. Okay, so that'll help you you can now go backwards. Instead of multiplying by that, you can divide by that. And we know how to divide by fractions. All right, that takes care of 16. Let's go up here and see what were the other ones. 16, 18, and 22 through 25. Okay, so 18 is decide where these are true or false. Is this true or false for all real numbers? Is the cube root of x cubed equal to x for all real numbers? Okay. If you went back to part A, I think they had one with a square root. So they would say something like the square root of x squared is equal to x for all real numbers. And that would have been your chance right there. So don't be surprised if that one shows up on a test, because it's very similar to me asking if the absolute value of x is equal to x. And we know that that is true sometimes. This one is also true sometimes, and it turns out for the exact same reason. The square root of x squared, if you watch the other video or you saw it in the textbook, is actually equal to absolute value of x. And we know absolute value of x is equal to x sometimes. So I'm trying to make those connections. Hopefully that works out. Okay. And then I said 22 through 25. And let's see what those look like. 22 through 25. Okay, so we've got a determine which of the following are irrational. So they are expecting you to kind of do a little simplifying here first, not just grab a calculator. Your calculator isn't going to really help you with these, because if it's irrational, that means it has to go on and on forever, never repeat, never terminate. But that's almost impossible to see on your calculator. In fact, if you were doing the section 7.3 homework and you were trying to find 4 over 19, your calculator would make it look like it's irrational because it doesn't seem to repeat. It does repeat just after 18 digits, which is too big for your calculator screen. So we can't use our calculator to check these. We have to do a little bit of work, and they're asking you to do things utilizing what they've covered in this section. So the square root of 320 over 20, I mean, that is really just saying 320 over the square root of 20 is the same as the square root of 320 over 20 using that property of exponents. So try that as a way to kind of simplify. Here, you could do square root of 50 is the square root of 5 times the square root of 10. Maybe you could factor that out in front and see if that helps you to determine whether it's irrational or not. Okay. Down here, I'm adding things. They look like fractions. Get a common denominator then. Don't let this stop you because there's a square root of 2. You can still get a common denominator and then subtract. True or false? Hey, these are, it might as well be always, sometimes, never. The set of real numbers is closed under subtraction. The set of real numbers is closed under multiplication. Okay, so these are those, though, because there is the set closed. That would always, it would only be always or never, because it either works all the time or it doesn't work all the time, right? So there would be a difference here. If I wanted to do an always, sometimes, never, I might say take two real numbers and say x minus y is a real number. Okay. And you would have to say, oh, yes, that is always true. If it's closed under multiplication, I would say x times y is a real number. And you'd have to say, is it always true, sometimes true, or never true? We know multiplication is a closure with the real numbers. Again, if it was like x divided by y is a real number, then you'd have to say sometimes, because with division, we got to be careful because we cannot divide by 0. So keep that in mind. All those pieces stay true. Part C, I'm pretty confident they made a typo here. I'm like 900% confident. I believe they meant a times b equals 0. If a times b equals 0, then a equals 0, b equals 0, or both equal 0. Okay. So that's kind of what they're looking for there. Find the missing value in 24. These are proportions. Use your proportional reasoning. So you can either do the find a common denominator. You can flip things around if you want to. You could use because they're ratios, solving a proportion, you could use the cross multiplication technique, which, if you really look at it, folks, is just finding a common denominator. So if you had 1 over x and it's equal to x over 7, and in your mind, you're going to tell someone to cross multiply, remember, all you're really doing is finding a common denominator and then comparing the numerators. So when you think, oh, I'm going to multiply up this, I'm going to multiply up that way. Yes, the result is there. And that is a technique that shortens it down, but it takes away from what you're actually doing. And it means that sometimes students will misuse this. Students will misuse this when they're doing a problem like this. Don't be surprised because you showed them how to do that if they suddenly come up and say 8 plus 3 is 11. Okay, don't be surprised at all. All right. So again, cross multiplication, I'm not a big fan of that terminology. I just think it gets misused, so be careful with that. And lastly, order the following from least to greatest. This one changed it up. It went from smallest to biggest. I think in the past, some of them were from greatest to smallest. So just make sure you read that correctly and write out the digits if you need to. Your calculator should have pi on it. If it doesn't, turn it sideways if you're using your calculator on your phone. If you're using a standard calculator, there should be a button somewhere on the calculator that's either like a main button or it's like a little thing that's written above it. And if it's above it, go for the button that says second, or maybe the button at the top that says shift. Okay. So take a look at that as you're doing it. And I'm going to write down their typo here because that's pretty sad. Kind of a big one there. If A times B, if A times B. Oh, goodness. Oh, what page is this? Page 422, question number 23C. If A times B. And they mean if A times B equals 0. Okay. Good gracious. All right. Well, that about does it for this activity. So hopefully that takes care of it. That was your last homework set for this term. We'll have more when we get into Math 106, but that'll do it for now. All right. Off you go.